So, continuity. With continuity, a function can be continuous, which means on an open interval, the function never stops, never breaks. So this is where, so there's no asymptotes, holes, jumps, or anything like that. Imagine you can, or at least there's no vertical asymptotes. So imagine there's a function. This function is plotted on the ground. For example, if we do y equals x. If we plot this function on the ground, you can walk across it. And there's no point where you have to step off the function. But if you have, let's say, a piecewise function, where f of x equals x plus 1 for when x is less than 1, and let's say it equals 7 when x is greater than 1. Well, if we have this function, it will be x plus 1, just moving about here, for x is less than 1, then at 1, let's do this greater than or equal to 1, then at 1, when it hits 1, it will equal 7. This jump means that you can no longer walk across it. Or if there's a function with a hole, if the function has a hole in it, you'd have to step over that hole. That is a simple way to explain what it means for a function to be continuous. Now, a few ways you can decide if a function is continuous or not is 1, if there is a vertical asymptote, 2, there is a hole, and 3, this applies to mainly piecewise functions. This is the main point in which you use it. There are 3 rules you must follow. First of all, at a certain point A, f of A is defined. So no holes. 2, the limit of f of x as x approaches A exists. So simply the limit is there. So if we have a jump, the limit does not exist. Therefore, it's not continuous. 3, the limit of f of x as x approaches A equals f of A. So if we have a graph where it looks something like this, and then it hole right here, and it jumps up here, right here, this is a situation where this limit exists, A is defined, but it does not equal A. And I'll cover 3 examples where each of these rules is violated. For 1, f of A is defined. So if we have a piecewise function, f of x is equal to x plus 1 when x is less than 1. So when x is less than 1, and then it's going to equal 2 when x is greater than 1. So if we were to plot this out, it would be x plus 1 for when x is less than 1. You get to that point where it is going to be, where then you get to at 1, there's going to be a hole there because the function is not defined at that point, and then it's going to equal 2. It's going to flatline out. Now, the limit exists because from both sides it's approaching 2, and the limit of f of A, well, doesn't equal f of A because f of A doesn't exist. So this is where that first rule is violated, and also the third in this case, because there is a hole. It doesn't exist. There is no point there. Now, another time in which a limit does not exist is, like I said in one of my previous ones, it's x plus 1, f of x is equal to x plus 1 when x is less than 2, let's say, and then it's going to be equal to just 8 when x is greater than or equal to 2. Now, at this point, every f of a is defined. Any point you get, specifically this break in between the two functions, you can plug in 2 and it will be defined. It will be 8. But if we look at our graph, it's going to hit a point, right? There's going to be a jump where this right here, this point is defined, but the limit does not exist. This is because the right-hand limit, right, when it's coming in from the right, it's approaching 8, while when it's coming in from the left, it's approaching 3. Now, so this means that the limit does not exist. So now our final example is the limit of f of x equals f of a. So if we were to do an equation where when x is greater than 2, it also equals x plus 1. X plus 1. So these two, but it equals 8 when x equals 2. So if we were to plot this, it would go almost a straight line, hit that point where it is at 2, right? And this point is at 3. And it would hit a hole. And it would continue on. But at this point, x would be equal to 8. So f of x is defined. The limit exists because it approaches 3. As x approaches 2, it approaches 3 from the left and right. But the limit of f of x, so the limit of f of x will be equal to 3 as x approaches 2. So the limit will be equal to 3, but f of a is not. F of a is equal to 8. So because these two don't equal, the function is not continuous. And back to my original rule that I described at the beginning, if you were to walk across this, you would hit a point at which you'd have to crawl. You can't just stay on the function. You have to jump up here, then jump back down here. Which is the third, and that's the third reason a function could not be continuous.